Yes, thank you for the introduction. I hope everyone can hear me. I'll try to share the screen.
Yes, we can hear you. We can see your slides. Thank you.
Okay, so if it's okay, I can start.
Please go ahead.
Okay, so hi everyone. Today I will introduce you a joint work with Maxime Folschette, Magnin, and Katsumi Inoue, which title is very long, so let's just say that it's about learning dynamics from any semantics. So I will start by a quick motivation about learning system dynamics. Then I will discuss about the problem arise by tackling several dynamical semantics, and finish with giving some hint about how to learn from any of them. So first, what we are doing. So we are given a set of input and output state of a black box system, and we want to learn its internal mechanics. So we observe a system from the outside. We cannot have a hint from the inside. And more precisely, what we consider as discrete system. So the input and output are actually vectors of same size, but contain discrete value. Just to be simple, they just are vectors of integers. And we consider dynamic system. So it means that the input and output are actually the state of a system, and an output become the next input of a system. And you loop like this and so on. So our goal is to produce an artificial system that behaves the same as the one we observe. So what some people call a digital twin in the industry. And the representation we use is a logic program. And to be more precise, we use propositional logic program with an allocated atom in order to encode multi-valued variables. So the setting are like this. So we have our data, we have a data about some black box system, and we have only some of them. We have a black one, and the gray one, we don't see it. What we want is to learn a logic program that is able to reproduce the black one, also the gray one, so the one we didn't saw, and also explain every observation. So for example, here, these two rules in blue, they explain the transition in blue. So we want a model that can predict and also explain. So the main motivation comes from biology. So a typical thing we can do is construct gene regulatory network. So we'll have data from, for example, some microarray that will be time series of gene expression. And what we will want is to have some kind of graphical model that biologists like Boolean networks, and that will give information about the whole behavior of the system and also explanation about each observation. So for example, here, this transition 0, 0, 0 to 0, 1, 0 was caused by the influence of C on B, that is an inhibition. Here you have another observation, another explanation, and so on. But our work is not limited to bioinformatics. Actually can be applied on any discrete dynamic system. For example, we did some collaboration regarding robotics. And here observation could be observation of environment evolution according to robot action. So we'll see a robot moving around in some scenes, and according to the action, the environment will change. And that's the kind of thing we will learn. So it's important to say that we learn the rule of the environment. We don't learn a strategy. For example, if we had observation about chess, we will learn how to move pieces. We will not learn how to win. So that's the idea. So let's see about the problem regarding dynamical semantics. So here you have an example of very simple Boolean network where you have just two variables that inhibit each other. You have a Boolean function here. And according to the semantic you are using, the transition of the system will not be the same. So basically the semantic dictate how you update your variables. So if you consider a synchronous semantic on the left, you will update all variables at the same time, and you will get this kind of transition. If you consider an asynchronous semantic that is quite popular in biology, here you consider only one variable can change at the same time. So some transitions are not possible. For example, you cannot go from 0, 0 to 1, 1 because you need to change two things at a step. And the general semantic, which is the third one that is also considered, which is a kind of generalization of the two. Here you can change any number of variables at the same time. So you have different observations that can come from the same system. And so far in our work, we only consider synchronous deterministic semantic. And now we propose a way to tackle learning from any of these three, and actually much more. So first, what is the semantics? So for these three semantic, at least the one I just showed, it's just about computing the next state by selecting what rule will be actually applied. So it's like if your black box system is actually composed of two parts. You have the rule of the system. So like in chess, you have the rule for each pieces, and you have a rule of the semantics, that's a kind of meta rule. You cannot move a piece, more than one piece at a time, this kind of thing. So the idea is that if we are able to learn the blue part, then we are independent of the red part, and it's a win. Okay. So what is the blue part? What is an applicable rule? Actually, it's just a condition so that a variable can take a certain value in the next state. So that's equivalent to a classification problem. So we can just take our observation, so the state transition of a system we have, and for each variable value, we will have positive example and negative example of the occurrence of a variable. So if you have some, so here you see in blue, you have a typical state where A0 is observed in the next state. So you can observe here and here. And in the red one, the negative example, we never observe A0, for example. So you do that for every variable, and you get a classification problem. And if you learn a model from this, it will be independent of the semantics, at least these three. So long story short, we have an algorithm for that, but I don't have time to give a detail about it. So please check the paper. I will give a link at the end. And given these three example of transition set, it will output these three programs. So in the first one, in the synchronous transition, you can see the rule that correspond to the original Boolean function. So A if not B and B if not A. In the asynchronous and general case, you find them also, and you have additional rule that captures the fact that because of a semantic, a variable can keep its value. So we capture these three semantic and actually much more. So one thing we did in the paper is to characterize the class of semantic we capture. So it's a semantic we call pseudo-idempotent. So I will not go too much into detail, but if you consider a semantic as a function, it takes a feature state as input and a set of atoms that actually are the head of the rule that match the feature state. And it produces a set of target states. So semantic produce transition, basically. So if you take this target state, you make the union and you apply the semantic again. If you find the same target state, then we call it a pseudo-idempotent semantic. So you have a property below. So any semantic that respects that is captured by our algorithm. That's the idea. So, but what about other semantics? What if it's not pseudo-idempotent, or what if we have even no idea about the semantics? So here are three examples of arbitrary semantics. So in this one, we have the semantic applies a rule, but it changes every variable at the same time, and sometimes it changes nothing for some reason. Here another example. So you apply the rule of a system, and sometimes you can have a degradation. So a 1 can become a 0 at any time for some biological or system reason again. And here a third one where you can at any time inverse all value of a state. So how can we learn a program able to reproduce such behavior? So how to be independent of any semantics? So the first idea we had is let's just apply the algorithm we have on it and see what we get. And since we don't know the semantic, just apply the synchronous one, because why not? And if you do that, so from the black transition, you will learn a program. And if you apply synchronous semantic on this program, you will reproduce the black one plus additional red ones. So we have everything we want plus some additional thing we don't want. So the game is just to avoid this red one. So how to prevent them? Actually, there is a way just to use constraints, and to use them, we need to learn them. So again, long story short, it's a matter of modelization of observation. So we can actually use the same algorithm to learn constraints by using the observation as negative example. Because what is a negative example of the application of a constraint is the actual observation, that's the idea. So we just take the observation and encode it as a kind of meta state that we will consider as our negative example, and we learn rule from this. And the rule we learn are actually constraints. So we will obtain this kind of thing. So we will have like the rule of the system, some conservation rule, and the constraint that prevent the red ones. So that's the idea. So conclusion. In our previous work, we only consider synchronous deterministic transition only. And now we can tackle any memoryless discrete dynamical semantic. The main application is that the selection of a semantic that can be quite boredom for biologists now can be done a posteriori. So the biologist just come with his observation, run the algorithm, he get a model, and then he can play with it. If he don't know the semantic, he can even learn some constraint and get some hints about it. So that's the idea. The weakness, of course, is that so far it's an exact method, so it's very costly and sensitive to noise. So to deal with real system, we need to do some heuristic approach. The source code is available as open source on GitHub. You can find it with a QR code link on the right. And if you want to see all the detail about the theory, you can look at the manuscript with the QR code on the left. And if you have questions, please join us at the poster session this afternoon. We have 2 papers, one which is about the theory, the paper, and one which is about the biological application. And that's all. Thank you.